Hello, in this video we're going to start looking at simple harmonic motion, which is a particular type of oscillation and a way of describing what is a fairly common type of oscillation that occurs in the world. So it's useful to be able to describe it, and as the name suggests, it's relatively simple, so it's a good place to start. Right, so let's take one quick step back before moving forwards and think again about what we mean by an oscillation. So we've got some particle, whatever it may be, and it's moving from side to side. It's oscillating backwards and forwards. So it goes off to the right, say, and then it reaches our maximum distance away from where it started at this equilibrium position, reaches some distance A, then it goes back towards the equilibrium position out the other side by distance A, and then it goes back again. So it's just going backwards and forwards, backwards and forwards. And we've got this equilibrium position here in the middle, the point that the particle is oscillating about. So we must have forces going on here. We must have, if the particle, when it starts moving off to the right, is going to slow down, stop, and then go back again towards the middle, there must be some force which is acting towards the equilibrium position. And similarly, when it goes off to the left, there must be a force acting back off to the right towards the equilibrium position. So there's some restoring force, and as suggested by the name equilibrium position, that there is no force when the particle is sitting at this midpoint, at this equilibrium position. So if we just left it there, it would just stay there because there's no force acting on it. But if you move it off to the side, then there's a force pulling it back again, back to the equilibrium position. So we need to think about the forces that are involved in oscillations, as well as the motion. So where is it as a function of time? What is its position as a function of time? The velocity is clearly changing because it's going backwards and forwards. So we want to describe the velocity as a function of time. We've got these forces acting. We want the acceleration as a function of time. So we want to describe all of those things. And then, of course, we've got the other stuff that we were talking about in the previous video, where we want to be able to describe the amplitude, as in the maximum displacement, things like the period or the frequency of the oscillation, just so we've got convenient ways of comparing things and describing things in the world of oscillations. Right, so now let's come back to simple harmonic motion and what this actually means. So simple in simple harmonic motion just means that there is a single force acting on the particle. Now that force will be variable, obviously, because it's moving backwards and forwards. So the force will be changing direction, but it's one type of force. It's only coming from one source. We're not looking at multiple sources of forces that are causing the oscillation. I mean, there might be more than one force at play. Like if you've got a spring with a mass on it, clearly we've got gravity in play here. We've got the weight of the particle acting downwards, but it's not the weight on its own is not causing it to move and oscillate. If you just left it with the weight, it would just hang in an equilibrium position. It's when we offset it and we get the spring is then causing the oscillating motion. So you can have more than one force at play. Same on a pendulum. Again, we've got the weight of the object at the end of the string, but it's the component of the tension in the string which is restoring the object back to the equilibrium position. So it's not to say we've only ever got force diagrams with a single arrow on. That's not the case, but we've got one force is causing, it's driving the oscillation. That's the single force that's acting. So that's the simple part of it. The harmonic part of it is saying that the oscillation is sinusoidal. So we can describe it either with sine or cosine. I mean, they're essentially the same thing. They're just shifted by 90 degrees or pi by 2 in one direction or the other. So these are the same function, really. It's the same oscillating motion. You know, when you draw a graph of sine x or cos x, and you've got this same motion going on here. So this will be a description of, say, you know, if we were going to draw out displacement s against time, then this would describe how the displacement is changing. And of course, it's also going to be describing how the velocity is changing and the acceleration is changing, but we'll get onto that in a moment. So when the particle is passing through the equilibrium point, it's got the high gradient, it's going through the point very quickly. That's where the velocity is maximum, or the speed is maximum, depending, you know, because it's going to be going in both directions. So when we get towards the end, it starts, you know, slowing down as it reaches the amplitude. It momentarily stops, and then it starts going back in the other direction. So that's what the simple and the harmonic bits mean in simple harmonic motion, that we can describe them in this way. And this makes things a lot easier in a lot of ways, because a lot of things drop out of this. You know, why have we decided it's going to be harmonic? Why have we decided we can describe these as sine waves? Right, well, let's start off first of all of just assuming that we can, and then we'll see why this is particularly useful. So we could say that our function of displacement as a function of time is equal to, well, let's say it's some sine function, and let's write the completely general form of a sine function. So we'll put some multiplier at the start. It's a function of time, so we'll have some multiplier of time inside the argument here for sine, and we'll add on some amount as a shift. This is like doing transformation of graphs. You know, what can you do rather than just saying, well, we've got sine of t? How can we change it? Well, we can stretch it. We can in two different directions, whether it's this direction here or this direction here. We've got two ways of stretching things, you know, an x stretch and a y stretch, and we got an offset. So we got an offset there, that would be an x direction translation, and then we could add on something in the y direction. So we got two stretches and two translations. So that's our most general form of the of a sine function. So if we want to get velocity as a function of time, well, we just differentiate this, and then we see what we get with that. So we're going to get an a omega cos omega t plus phi, and then this constant's going to disappear. So we've just taken this omega out from inside the sine function, because that's the multiplier of t. And then we can differentiate again to get acceleration as a function of time. So we have minus a omega squared sine omega t plus phi. And you'll see, with the exception of this S0, so if we had made this initial displacement 0, so we focused everything on, I don't know, say it starts at the equilibrium point or whatever, we've got quite a similarity here between displacement and acceleration, because this is minus omega squared times s. So we've sort of come round in a full loop by differentiating things, and that's what we know we get when we differentiate sine and cosine. You know, the gradient of one is the value of the other. So yeah, we can go round in this loop. Right, so why is this going to be useful? Now we can come back to the details, and we will do, of all of these different terms in it, but let's stick with this bit first of all. We've got the acceleration is proportional to the displacement, and of course acceleration is also proportional to force. We know this from Newton's second law. So do we have any situations where force is proportional to displacement? And yeah, of course we do. I mean, there's probably one thing that's immediately jumped into mind, and that's Hooke's law. So in Hooke's law, we know, and this is why we're getting onto things like springs. In Hooke's law, we've got that the force is equal to k times x, where you've got your spring constant k, but the force is proportional to the extension. We've seen that when we draw out our graphs. We get F against X, and we've got a straight line. So this immediately fits in with what's going on. If we were going to look at a spring and say, okay, we've started off with forces proportional to extension, I mean, okay, well, the acceleration is going to be proportional to the extension then, and then we could work backwards and we're going to get exactly the same thing, because you said, well, what thing can we differentiate twice in order to end up more or less back where we started? So sine waves immediately spring to mind. And this is where we're getting this harmonic part of the motion from, and that's why we're looking at SHM. And we'll see this turns up in loads of places, this force proportional to displacement. Right, so this is all good. Now let's take a closer look at these three equations, so we can get a better understanding of what's going on with all of this. So I've just written out displacement A sine omega t plus phi, and we need to dig into why I'm using all of these letters, which is fairly straightforward once we get into it, but it's a discussion we need to have on all of this. So these are all of the ones that I just wrote out on the previous page where I was differentiating everything, and then of course we saw that the acceleration is equal to minus omega squared s. So let's start with this one at the top with the displacement. And why have I used all of this? So from an oscillating point of view, we've got some particle. It starts, say, at an equilibrium position, moves out, stops, comes back, then moves out, stops, comes back. And it just keeps on doing this. So it's going in this back and forth fashion. And we've said that this is going between amplitude minus a to plus a. So we're measuring a displacement, so it's vectors here. We're not just saying it's a either side. We've got to have a negative direction, so I've taken negative to go off to the left. Now let's look at our displacement function over here. Well, the sine bit of this is going to be varying between -1 and 1. So we have got the displacement varying between minus a and a. So that's why I've used a here, because this must be the amplitude. That falls straight out of our description. Right, the stuff inside the bracket here for sine, we need to go back to circular motion as to why we've got all of this. So let's think back to some particle on a circle moving around with angular velocity omega. So that's our radians per second. Let's say that's our 0 angle here. So it started here, that's at 0, because remember with circular motion we're measuring angle going round. So we have to have some line that we measure the angle from. And it starts off here at time t equals 0 at some angle, which we're going to call phi. Let's say now after time t, we've moved through an additional angle theta. Well, theta, so angle is angular velocity times time, so that's omega t. Now let's specify well, in this case I'm going to stick with a y coordinate, but I'll also give a nod towards the x coordinate as well. So say the radius of the circle is a, the y coordinate of this particle is going to be a sine theta plus phi, and theta is omega t plus phi, which of course is exactly what is written up here for the displacement. The x coordinate is going to be a cos omega t plus phi. And I could have written up here, this bit, I could have put cos here rather than sine. Hasn't really changed anything if I put cos in there instead of sine. All I get is that would be a cos. I then have minus sine here, and then I'd have minus cos here. Doesn't change this final equation that the acceleration is still proportional to the displacement. And this is what we'd expect. Remember when you're drawing your sine and cosine graphs, so sine and then cosine, these are just, it's the same shape of graph, it's the same function, it's just been moved by pi by 2 in the x direction. So it's just a transformation. And a transformation in the x direction is just changing this phi on the end here. That is a translation in the x direction. That is all it is. So if we change that phi, well, yeah, I mean, that's just saying, well, let's change the starting position. You're more or less rotating your axis. It's like taking this 0 and saying, well, okay, if we have our 0 position there, well, maybe we want to have our 0 position down here. So we've changed phi, and all of a sudden we're now going to be getting, you know, looking at cos rather than sine. There's no difference between what we're picking here. Sometimes this confuses people because they'll see definitions of simple harmonic motion in, say, a formula booklet or a textbook, and they keep flipping these functions around. Sometimes they're using cosine, sometimes they're using sine. Doesn't matter. If you want to change from one to the other, just add pi by 2 onto here and you flip to the other one. So we don't have to worry about that. But now let's get back to this equation then, this y coordinate. So we're describing the displacement here of this particle that's just moving side to side is a slice through circular motion. This is the coordinate, the y coordinate of this circular motion. It's just taking one dimension through a particle that's moving in a circle. And it's giving us the meaning now of everything that's in this equation. So the amplitude here, A, is the radius of the associated circular motion. So that's our radius. This omega is the angular velocity of the circular motion. And then the omega t plus phi bit, which we're taking the sine of, that is equal to what's known as the phase. And the phase is just describing, well, how far round the circle have we got? Or from the point of an oscillation, how far through the oscillation are we? And we describe this in terms of 0 to 2 pi, because we're going around one circle. So one circuit, one lap of this circle is going from 0 to 2 pi in terms of the angle. So we do the same with the oscillation. We could say, okay, it starts at 0, it goes out to here, it's at pi by 2, it comes back to 0, it's now at pi, because of course that hasn't completed an oscillation, because when we started it was going to the right, but pi is now going to the left. So to get back truly where we started, we now have to go off to this side when we're at 3 pi by 2, and then back again. So we're at 2 pi when we return to the equilibrium point, and we're going off to the right in the way that we were when we started. So we can describe the position of the particle where it is within its oscillation. So not an actual, oh yeah, it's 5 centimeters to the right, not that sort of position, but how far through an oscillation is it? It's 3/4 of the way through the oscillation, so it's at this phase of 3 pi by 2. This also allows us to talk about something called a phase difference. So if you've got multiple particles all oscillating in the same way, but they've all been offset from each other, like they've got different phis, they've all started at a different position, but they're still, everything else about their motion is the same. They're just oscillating, in the same manner about the same point. Well, we can talk about the phase difference. That's just the difference in the angle. So, if one of them is just starting while the other one has already reached the first amplitude, we've got a phase difference of pi by 2, because this one's at phase 0 and this one's at phase of pi by 2. So we can talk about phase difference as well. So all of a sudden, by thinking about circular motion, all of these terms in here, they all mean something. They're all directly relatable to circular motion. Now let's have a look then at the velocity. We can say that our maximum velocity, when is this going to occur? It's going to occur when the phase is equal to 0 or to pi, because we want the cos to be 1 or minus 1. If we're looking for maximum magnitude, so maximum speed, so if we got that to be a maximum, then we want cos to be plus or minus 1. So we got a maximum velocity of a omega. And of course, that is going to occur for cos at 0, pi, 2 pi, etc., etc. So it's telling us then that we're getting maximum velocity at the equilibrium point, because that's when we're at 0, pi, 2 pi, and all the rest of them. So that's when we've got I'm writing a completely different word there. I was meant to be writing equilibrium. I think I was writing equivalent or something. Anyway, at equilibrium point, that's when we get maximum velocity, and it's a times omega. So that's useful. Actually, I suppose that's something we could have said here. Although we know maximum displacement, I know it's obvious from the picture, maximum displacement is a, the amplitude, but we can also see when that occurs. It's going to occur when sine of the angle is equal to 1. So at multiples of pi by 2, because that's when sine becomes 1 and minus 1. So our maximum displacements are occurring then. So again, it's all fitting with our picture. Now we can come and look at the acceleration. So our maximum magnitude of acceleration, that's going to happen at the same points that we've got maximum displacement, because we've got a sine function again. So that's going to happen at the amplitudes. And that maximum acceleration is going to be minus a omega squared. So all of this stuff is just dropping out. We've also got, of course, that we're measuring whatever direction the displacement is, the acceleration is in the opposite direction, because we've got this minus sign here. So if we're at a maximum amplitude, positive amplitude, we got maximum negative acceleration. So that just fits in. We've moved off to the right in a positive direction. We've now got a maximum restoring force going off to the left, which is the negative direction. And similarly, if you go off to the left, where we got maximum negative displacement, we got maximum positive amplitude. So all of this stuff has just suddenly come into view, and the whole thing just makes sense by looking at all of this. And okay, you want to know your calculus, so we can move up and down these things, but this is just the general description of a sine function, of a sine wave. So providing you've got that and you're happy with trig calculus, and you're happy with transformations of graphs, because that's all we've done to it. We've added all the transformations in here, the A, the omega, and the phi. Then SHM is simple. There's nothing else you need to really know about this. You've got epically powerful analysis techniques at your fingertips. And it all because of this link back to circular motion. And we're going to find that a lot of things move in SHM. And very close to SHM. So we're going to see this with pendulums, mass on a spring, electromagnetic waves, alternating current, loads of it. It's all stuff that is actually simple harmonic motion, or very close to simple harmonic motion. So yeah, it's wonderful stuff, very powerful.